Hi everyone, welcome back to another Hackerrank series where I try to do these questions right in front of you guys. I've decided to change up the strategy a little bit. Like I will at least skim through the question before I jump into it because I don't want to think about because the questions are getting a bit harder now and I don't want to waste your time by just scratching my head in front of you. So yeah, I just read through and once I was confident I kind of understood the question, I decided to make the video. So yeah, let's read the question. I'll just read again and explain to you what the question requires us, and then I will code it out. So you'll be given a list of integers, ARR, and a single integer k, and you must create an array of length k from elements ARR such that its unfairness is minimized. So from this, just the first two lines, what we are getting is that they give us an array and we can rearrange it however we like, and we need to come up with the sequence. We need to choose some items from it such that we need to choose k items from it. Wait, yeah, we need to choose k items from it such that the maximum of it minus the minimum of it is the smallest. That means the unfairness must be the lowest. So let's just go through a simple example right now just to understand the question. If k is equal to 2, I can look at all of these things, but if we rearrange it, let's just keep it simple. Let's rearrange everything. Let's sort everything, because a lot of times when we have these kind of minimum maximum optimization questions, a simple sort would go a long way in helping you understand the question. So let's try to sort it out, and let's pick 2. So we need to find something that has the lowest unfairness. So testing for all pairs, the solution 1, 2 provides the minimum unfairness. So let's look at 1, 2. 1, 2, the maximum is 2, the minimum is 1. Minus these 2, you get 1. Let's go to 2, 4. 2 is the lowest, 4 is the highest. So 4 minus 2 is 2. This one, 4 is the smallest, 7 is the largest, 7 minus 4 is 3, which gets worse and worse. So we can say conclusively that the first two, which this was the best case, and that's why they returned this as the answer. 1, 2 provides the minimum unfairness. Likewise, the main trick to this question is that you can select anyone. It doesn't need to be in this specific order. You can rearrange them, and hence a very good idea to take note of in these kind of situations is just think about it. Like, does a sort help you? So that's what I'm going to do now. Okay, before that, let's just print it out and see what we get as usual. ARR, no, ART. I'm running it. Yep. So it gives me 3, which is the size, which is the number of items that I must choose for the unfair, for the ARR prime. So I can choose these 3 or these 3. Like I can choose any 3. It doesn't need to be in sequence. It doesn't need to be contiguous, or how you want to pronounce it. So this is what I'm going to do. I am firstly going to sort the thing. So let's say ARR is sorted ART. And the next step is the reason why sorting helps us in this case is because a lot of times in this, we need to do a max and a min. If I were to just traverse through this like 1, 4, 7, 2 to find some kind of pattern, if I were to do this, I need to go through each one to, let's say a slightly bigger 6, 8, 9, 12. And let's say I have to compare 5 items and I do a min or a maximum operation. This is very costly if the number is really, really big, and we will fail in terms of time limit exceeding, or some kind of error will be there because we are not efficient enough if we are trying to do this. Like min and max both operate at n time complexity. So if I were to do a min to compare each combination, I'm doing n times whatever, like whole total length of things minus k complexity, which is just massive. So to avoid this, an idea that we have is we sort it out first. if we sort out everything like 1, 1, 2, 3, 4, 5, I will always know that the smallest item will be the first index, while the largest item will be the last index. And from which I can just go one by one. The next smallest would be this, and the next largest would be this. The next smallest would be this, and the next largest would be this. And the difference between these two would be the smallest. Like, think about it. This with any other item, like in this side, would be definitely bigger for the unfairness score. And hence, assorting helps us a lot. Okay, I've explained quite a bit. I will now start coding. So the benefit of this strategy is that I will always know that the first index is the smallest and the last index of the selection is the largest. So I'm going to do this for I in range len arr minus k. Is it minus k? Okay, let's do a simple calculation. Let's say I have 1, 2, 3, 4, 5, 6 items, and I want to traverse 4 times. Like I want to select 4 things. So I have 1, I have 2, and I have 3. So I need to run 3 times. So out of 6, after minusing 4, I need to plus 1 so that I can run 3 times. I'm just trying to count how many times do I need to run through to make sure all of them are selected. So len minus arr will give me 6, which is this thing. Minus k will give me 2. I just need to plus 1 more to make sure that I ensure that I've seen all of the items that are present in the array. Okay, so for I in range len arr minus k plus 1, I'm basically creating a new list. List is equal to arr I plus k. This one I don't need to minus 1 or plus 1 over here. The reason being that it'll automatically just look at the one before it ends, which is how indexing works, index splicing works. So yeah, I and I plus k. And what I'm going to do is I'm going to see if this is the smallest. So first thing I need to do is smallest is equal to, let's see the first, I'm going to just see what's the first, like the first type, what the first type returns to us. So smallest is equal to arr. The biggest item in the first selection would be k minus 1 minus a, the first item. So the reason why I do k minus 1 is because k, if it's 4, 0, 1, 2, 3, 4 will be the beyond the scope that I'm looking for. So I need to do k minus 1. So arr k minus 1 minus arr 0 will be the smallest. And if you want to just make it a bit more efficient, you can do this because we have already seen the smallest one over here. I don't need to repeat it over here, like by putting I is equal to 0. So I can just start with 1. Because in effect, this is essentially when I is equal to 0, like I is 0. Okay, now what I'm going to do is I'm going to compare them. So smallest will be the smallest of itself and the new calculation that I'm doing over here, which would be list 0. Okay, wait, this is the second part. Minus list, whatever is the largest in that list. In the new selection that I have, I'm selecting the last item versus the first item. That difference, I'm seeing if it is smaller than the smallest. If the new smallest is smaller than the current smallest, I'm changing the current smallest to the new smallest. Okay, that's, yeah, nothing too complex. Definitely. Just that when I verbalize it, I realize how yeah, ridiculous it sounds. Anyways, with that, I think we are done. So once I run through everything, this will be at quite a efficient time complexity because minimal time complexity, because as you can see, I only run through this number of times to get what I want. And this is sorted will run in quicksort, which is n log n. plus this thing, which is just plus n. This is not very computationally heavy. So let's see if it works. Yep, I passed the basic cases. And I'm passing. Hopefully I pass all of them. Do I pass? Do I pass? What? What happened? Okay, wait, hold up. Why? How much faster can I get? Okay. This is negligible because I'm just this is a constant because I'm just doing array indexing. This is, I already shaved it by putting the 1 over here. What more does it want? Is it this? Okay, yep, it's this. Like I'm creating a new array over here. Like this itself, this operation in itself, like creating a new array with this selection is quite computationally heavy, I guess. So an easy way to do this is we know for a fact it's this index and this index. I can just keep track of these indexes and then just keep adding one to it. So how it'll look like is, I'll delete this for now. ARR 0, which is, no, sorry, I, which is the smallest one, minus the largest one, which is ARR K plus I minus 1. Similar to this, instead we just adding an I to this sequence. So K plus I minus 1 minus ARR I. ARR K plus I minus 1. Okay, and then we just delete this. We don't need this anymore. And we run this code. And yep, we get the basic cases out of the way. And voila, we finished it perfectly. Perfect. I love it. So I love these kind of questions where it's so nice to see everything come together, and we might make some mistakes along the way, but we can always edit and figure it out. I didn't think that creating a new array would be that much more computational intense, such that just one test case fails it, which is why I was quite shocked. I was like, how can it be just one of them? So yeah, the strategy that I always employ is try to hit the most basic level first of conditions, then keep building on top of it. And after that, you can start shaving off the time complexity issues wherever possible. So, and Sorted is a tool that would be very useful in a lot of these optimization questions. And I highly recommend you guys checking it out or thinking about it when you're doing it. So yeah, that is my Hackerrank Maxmin. Hope you guys enjoyed it, and I'll look forward to seeing you guys in the next video. Peace. Bye.